In 1997, a theoretical physicist named Juan Maldacena published a paper. He was 29 years old. The paper was titled The Large N Limit of Superconformal Field Theories and Supergravity. It didn't sound like much to an outsider. But inside the world of physics, it was an earthquake. And Maldacena was working at Harvard University at the time. He was trying to solve a problem that had stumped everyone, including Stephen Hawking. The problem was about black holes and what happens to information that falls into them. He found a strange connection, a correspondence. He discovered a mathematical link between two very different kinds of universes. One universe was a lot like ours, in a simplified form. It had gravity, it had strings, it existed in a curved, saddle-shaped space called Onti de Sitter space, or ADS for short. The other universe was totally different. It was a flat, simple space without gravity. It was like the boundary or the surface of the first universe. The simpler universe was described by a type of physics called conformal field theory, or CFT. Maldacena's math showed that everything that happened in the complex 3D universe with gravity could be perfectly described by the physics happening on its 2D boundary. Every particle, every interaction, every law of physics in the 3D world had a direct equivalent in the 2D world. They were two different descriptions of the same reality. It was like a dictionary that could translate between two languages. This was the ADS-CFT correspondence. The implication was staggering. Our universe, with its 3 dimensions of space, could be a projection. It could be a hologram. The information that describes everything we see and experience might not be stored inside the universe at all. It might be encoded on a distant 2-dimensional surface that surrounds us. This wasn't just a philosophical idea, where it was a concrete mathematical model. It gave physicists a tool to study the hardest problems in science, like quantum gravity. It suggested that the solid 3D world we live in might be an illusion, a very detailed, very convincing illusion. Number 15, the universe just shouldn't be this simple. The universe's temperature is almost perfectly uniform at 2.725 Kelvin, no matter which direction we look. The cosmic microwave background radiation, the echo of the Big Bang, varies by only 1 part in 100,000. On large scales, the universe is also remarkably flat, not curved. Early cosmological models predicted a much lumpier, more chaotic, and curved universe. The early universe poses a huge problem. It's called the horizon problem. When we look at the cosmic microwave background, or CMB, we're seeing light from about 380,000 years after the Big Bang. Let's look at one patch of the sky, then let's look at a patch on the exact opposite side of the sky. These two regions are separated by about 28 billion light years today. When that light was emitted, they were much closer, but still too far apart to have ever been in contact. Light would not have had enough time to travel from one region to the other. So how did they end up at the exact same temperature? It's like finding two people on opposite sides of the Earth who have never met or communicated, but they're wearing the exact same outfit down to the last thread. It's incredibly unlikely to be a coincidence. The standard explanation for this is a theory called cosmic inflation. Inflation suggests that in the first fraction of a second after the Big Bang, the universe expanded exponentially fast. It grew from the size of an atom to the size of a grapefruit almost instantly. This rapid expansion would have stretched a tiny, uniform patch of space to enormous size. That would explain why everything is so smooth and flat, but inflation itself is a complex theory with its own problems. It requires a special kind of energy field, the inflaton field, that we've never observed. Holography offers a different perspective. Some physicists, like Leonard Susskind, suggest that the holographic principle could explain this smoothness without needing the full machinery of inflation. If our 3D universe is a projection of information from a 2D surface, then the rules might be different. The information on that 2D surface might have had plenty of time to mix and even out. The physics on the boundary could be much simpler. In some holographic models, the physics on the 2D surface does not have a concept of time in the same way our 3D universe does. The entire history of our universe could be encoded on this surface as a timeless static pattern. From the perspective of the 2D boundary, points that seem very far apart in our 3D projection might be very close. The information for two distant points in our sky could be right next to each other on the holographic plate. This could explain why they are so similar. They were never truly separate, they are just different projections from a unified source of information. This view simplifies the problem. Instead of a chaotic 3D explosion that somehow smoothed itself out, you have a more orderly 2D information field. The properties of this field would then dictate the properties of the projected universe. The smoothness and flatness of our universe might be a direct consequence of the nature of information on this holographic boundary. It suggests our universe's initial conditions weren't a random accident. They were determined by a more fundamental, lower-dimensional reality. The simplicity we see isn't a lucky break. It's a clue that we're looking at a projection, not the source code. Number 14, time itself might not be fundamental. An experiment conducted in 2012 at the Austrian Academy of Sciences demonstrated that quantum entanglement can occur between particles that no longer exist at the same time. The scientists entangled a pair of photons, then measured the first photon. The second photon was sent down a long fiber optic cable. After the first photon was already measured and gone, they chose what measurement to make on the second photon. The results still showed the spooky connection, as if the measurement on the first photon reached forward in time to influence the second. We experience time as a fundamental arrow moving from past to future. But in physics, time is more complicated. Einstein's theory of relativity showed that time is not absolute. It's relative to your speed. It can stretch and shrink. It's woven together with space into a single fabric called space-time. And in the world of quantum mechanics, some equations work just as well running backward in time as they do forward. The holographic principle offers a radical idea. It suggests that time, as we perceive it in our 3D universe, might be an emergent property. It might not be part of the fundamental reality. The true reality, the information on the 2D holographic surface, could be timeless. Think about a movie on a DVD. The DVD itself is a static object. All the information for the entire movie, the beginning, the middle, and the end, exists simultaneously on its 2D surface. There is no time on the DVD, but when you put it in a player, it projects a movie. It creates the illusion of a sequence of events, of time passing. The holographic universe could be like that. The 2D boundary holds all the information for our universe's entire history, from the Big Bang to the distant future, all at once. Our consciousness, moving through the 3D projection, experiences this information sequentially. That's what we call the flow of time. This idea helps with some deep problems in physics. The search for a theory of quantum gravity is the quest to unite Einstein's general relativity with quantum mechanics. They are two incredibly successful theories, but they contradict each other. One of the biggest points of conflict is time. General relativity treats time as part of a dynamic, flexible space-time. Quantum mechanics usually treats time as a fixed, universal background. If time is emergent, it could resolve this conflict. The fundamental 2D reality might not have time. Or it might have a different kind of time. The gravity and space-time of our 3D universe would then emerge from this timeless reality, just like the 3D movie emerges from the 2D DVD. The ADS-CFT correspondence, Maldacena's big discovery, is a concrete example of this. The theory on the 2D boundary does not include gravity. Gravity, along with one dimension of space and our familiar sense of time, emerges in the 3D projection. This is a strange and unsettling thought. It means the past is not gone. The future is not unwritten. They could both exist, encoded together on a vast cosmic boundary. Our sense of moving through time would be an illusion created by how we process the information of the hologram. It reduces time to a feature of our perception, not a feature of reality itself. Number 13, quantum entanglement ignores space. In 2022, the Nobel Prize in Physics was awarded to Alan Aspect, John Clauser, and Anton Zeilinger for their experiments with entangled photons. Their work confirmed that the spooky action at a distance that bothered Einstein is a real feature of our universe. They proved that two entangled particles behave as a single system, no matter how far apart they are. Or a measurement on one instantly affects the other faster than light could travel between them. And quantum entanglement is one of the most bizarre parts of modern physics. You can create two particles like photons that are linked. Their properties, like their spin, are correlated. If one spins up, the other must spin down. The strange part is that they don't have a definite spin until you measure one. And the moment you measure the first particle and find it's spinning up, you instantly know the other one, even if it's light years away, is spinning down. This seems to violate a core principle of physics locality. The idea that an object is only directly influenced by its immediate surroundings. How can one particle know what happened to the other instantly across vast distances? This is where the holographic principle offers a compelling answer. It suggests that things that appear far apart in our 3D universe might not be far apart at all. Physicists Mark van Ramsdonk and others have proposed that space-time itself is built from entanglement. The idea is called ER equals EPR. This stands for Einstein-Rosen-Bridges wormholes, are equivalent to Einstein-Podolsky-Rosen pairs entangled particles. It's a radical proposal that connects geometry and quantum information. It suggests that the very fabric of space is woven from the threads of quantum entanglement. The more entanglement between two regions of space, the closer they are. In a holographic universe, the information for our 3D space is stored on a 2D boundary. Two particles that seem light years apart in our 3D projection could be encoded by bits of information that are right next to each other on the 2D surface. Their connection isn't spooky action at a distance. There is no distance to cross. Their link is direct and local on the holographic plate. The apparent distance in our 3D world is part of the illusion. This completely reframes the puzzle of non-locality. It's not about faster than light communication. It's about a misunderstanding of what space is. You know, the space we experience is not fundamental. It's an emergent property of the connections between bits of information on a deeper level. The entanglement between two particles is a glimpse of this deeper reality. It's a crack in the holographic projection that shows us the underlying connections. This idea is being explored heavily in the context of the ADS-CFT correspondence. Scientists have found that creating and destroying entanglement in the 2D boundary theory directly corresponds to creating and destroying space-time geometry in the 3D universe with gravity. It suggests that the solid, empty space between you and the screen you're reading this on is not fundamental. It's a manifestation of a massive, intricate network of quantum entanglement. The universe isn't a container that things happen in. The universe is the connections between things. Number 12, gravity is the odd one out. Gravity is about 10 raised to the power of 36 times weaker than the electromagnetic force. That's a 1 with 36 zeros after it. If you have two protons, the electrical repulsion between them is vastly stronger than their gravitational attraction. You can overcome the entire gravitational pull of the planet Earth with a small refrigerator magnet. This huge disparity is known as the hierarchy problem of the four fundamental forces of nature: strong nuclear, weak nuclear, electromagnetism, and gravity. Gravity is the weird one. The other three forces are described beautifully by the standard model of particle physics. They operate through the exchange of particles, but gravity doesn't fit in. It's described by Einstein's general relativity, which says gravity isn't a force at all. It's the curvature of space-time caused by mass and energy, trying to create a quantum theory of gravity, one that describes it with particles called gravitons, is incredibly difficult. The math breaks down and gives nonsensical infinite answers. So why is gravity so weak and so different from the other forces? The holographic principle offers a potential explanation. In some holographic models, like the brain world scenarios inspired by string theory, the other three forces are confined to our 3D universe. Our universe is seen as a 3D brain floating in a higher dimensional space called the bulk. The particles and forces of the standard model are like strings whose ends are stuck on our brain, and they can't leave, but gravity is different. Gravity in these models is not confined to our brain. It can leak out into the higher dimensional bulk. The graviton is represented by a closed loop of string, which is free to travel off the brain. This would explain why gravity seems so weak to us. We are only experiencing a fraction of its true strength. Most of it is dissipating into the extra dimensions. This connects directly to the holographic idea. Our 3D brain is the boundary, the holographic plate. The higher dimensional bulk is the projected space. Maldacena's ADS-CFT correspondence is a precise example of this. The theory on the 2D boundary is a quantum field theory without gravity. The theory in the 3D bulk is a theory of gravity. This suggests that gravity is not a fundamental force like the others. It is an emergent holographic effect. It's as if the other forces are painted onto the holographic film, while gravity is part of the light projector itself. The weakness of gravity is a clue that it's operating on a different level of reality. It's not a force within the hologram, it's a property of the projection system. This would explain why it's so hard to unify with the other forces. We've been trying to fit a piece from the projector into the movie it's projecting. They don't belong in the same framework. This view turns gravity from a fundamental force into a thermodynamic or informational effect, a statistical outcome of the quantum bits on the cosmic boundary. Number 11. The math just works too well. In 1960, physicist Eugene Wigner wrote a famous paper called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. He was puzzled by the fact that abstract mathematical concepts often developed with no thought of a practical application turn out to be the perfect language to describe the physical world. Complex numbers, for example, were seen as a mathematical curiosity for centuries before they became essential for describing quantum mechanics. The universe seems to be structured by mathematical rules. From the Fibonacci sequence in a sunflower to the elegant equations of general relativity, the physical world is deeply mathematical. This is strange. Why should it be this way? Is the universe itself a mathematical structure? The holographic principle pushes this idea even further. It suggests that the universe is not just described by information, it is information. And information is mathematical. The fundamental reality is a collection of bits or qubits, quantum bits, on a vast 2D surface. The laws of physics that we observe are the result of the processing of this information. They are the algorithm running on the cosmic computer. This perspective helps to explain Wigner's puzzle. The universe is describable by mathematics because, at its core, it is a mathematical or computational system. The 3D world we see is the output of this computation. The laws of physics are not just a convenient description. They are a reflection of the underlying code. Take the ADS-CFT correspondence again. It is a purely mathematical duality. It's a set of equations that shows a perfect one-to-one mapping between a world with gravity and a world without it. Physicists can use this dictionary to solve problems they couldn't solve before. For example, they can take a difficult problem in quantum chromodynamics, the theory of the strong nuclear force in our world, and translate it into a much simpler problem about black holes in the other higher dimensional world. They solve the simple problem there and then translate the answer back, and it works. The answers it gives match experimental results. This is incredible. It means that a strange, theoretical, saddle-shaped universe with an extra dimension is mathematically linked to the real-world physics of subatomic particles. This shouldn't work unless there is a deep underlying connection. The holographic principle provides that connection. It suggests that both descriptions are valid because they are different views of the same underlying informational structure. The fact that we can use these abstract mathematical tools to make concrete, testable predictions about our universe is a powerful clue. It suggests we are not just observing a physical system, we are uncovering the rules of a computational system. The effectiveness of mathematics is not unreasonable. It's a sign that we are living inside a structure that is, at its root, mathematical. The hologram itself is made of math. Number 10, the observer changes the outcome. The double-slit experiment, first performed with light by Thomas Young in 1801, is the most famous demonstration of quantum weirdness. If you fire particles like electrons one at a time at a screen with two slits in it, they behave like waves. They seem to go through both slits at once and create an interference pattern on the detector screen behind. But if you place a detector at the slits to see which one the electron goes through, the wave behavior vanishes. The electron acts like a particle, goes through one slit or the other, and the interference pattern disappears. The act of observing changes the outcome. This is the observer effect. For decades, it has been a source of philosophical debate. What counts as an observation? Does it require a conscious observer? Most physicists believe it's about any interaction that extracts information. The detector at the slit interacts with the electron, and that interaction collapses the wave function, forcing the electron to choose a state. The holographic principle puts a new spin on this. It suggests that reality is fundamentally informational. A particle, like an electron, doesn't have a definite position or path until that information is registered or created. Before observation, the electron exists as a wave of possibilities, a cloud of potential information. The act of measurement is an act of defining a bit of information. It's like rendering a pixel on a screen. Before you render it, it doesn't have a definite color. The rendering process itself gives it one. In a holographic universe, the 3D world we experience is the rendered version. The underlying reality is the 2D information field. The double-slit experiment could be showing us the process of this rendering in action. The unobserved electron is still in its code state, a superposition of possibilities on the holographic plate. It interacts with the double-slit apparatus in a way that reflects all these possibilities at once, hence the wave pattern. But when you place a detector, you are forcing an interaction that demands a specific piece of information. Which slit did it go through? This interaction with the 3D projection forces the underlying 2D information to resolve into a definite state. The information electron went through slit A is now registered. This act of registration changes the system, and the wave behavior is gone. This view removes some of the mystery from the observer effect. It's not about consciousness. It's about information. Reality isn't a pre-existing movie that we watch. It's an interactive simulation that is rendered in response to interaction. Every time we measure something, we are participating in the creation of reality. We are setting a bit of information from a state of potential to a state of actuality. The world we see is not a static photograph. It's a dynamically generated image, and our observations are part of the rendering engine. The spookiness of quantum mechanics might be a direct consequence of living in a world that is being computed or projected in real time. Number 9, information seems to be the real substance. In 1948, Claude Shannon developed what we now call information theory. He defined the fundamental unit of information, the bit. A bit is a choice between two possibilities, yes or no, 1 or 0. This theory laid the groundwork for the digital age, but some physicists believe it's even more fundamental than that. They believe it's the groundwork for reality itself. The late physicist John Archibald Wheeler summed up this idea in the phrase, "it from bit." This means that every particle, every field, every force, the fabric of space-time itself derives its existence from bits, from information. The universe is not made of matter and energy, it's made of information. Matter and energy are just the way that information presents itself to us. The holographic principle is the ultimate expression of it from bit. It states that the total amount of information contained in a volume of space is not proportional to the volume, but to the area of its boundary. This is a radical departure from our intuition. We think of information as being stored inside things. But in the universe, it seems to be stored on the surface. This idea first came from black hole physics. Jacob Bekenstein and Stephen Hawking discovered that a black hole has entropy. Entropy is a measure of disorder, but it can also be seen as a measure of information content. They found that the entropy of a black hole, the total number of bits it would take to describe it, is proportional to the 2D area of its event horizon. This was the first hint that information in the universe might be fundamentally two-dimensional. Gerard Hooft and Leonard Susskind later generalized this idea to the entire universe. They proposed the holographic principle. The entire 3D universe can be described by information stored on a 2D surface at its boundary. If this is true, then information is the most fundamental thing there is. It's more fundamental than matter, energy, space, or time. They are all emergent properties of the underlying information field. This changes how we think about physics. Instead of asking, what are the fundamental particles, we should be asking what are the fundamental units of information and what are the rules for processing them. The laws of physics become the algorithm. The particles we see are like complex data structures in a computer program. A quark or an electron is just a pattern of bits. This view also offers a potential path to a theory of quantum gravity. Both general relativity and quantum mechanics can be thought of in terms of information. A unified theory might be found by starting with information as the primary concept and deriving space, time, and matter from it. We are not physical beings having an informational experience. We are informational beings having a physical experience. The world feels solid because the information is processed with perfect consistency, but the substance of that world is pure information. Number 8, our universe may have been born from a black hole. The singularity at the center of a black hole, where density and gravity become infinite, is a point where our current laws of physics break down. The singularity at the beginning of the Big Bang is also a point where our laws break down. These two singularities look very different. One is a point in space, the other is a point in time. But some theories suggest they are more closely related than we think. A theory called black hole cosmology, or the Schwarzschild cosmology, proposes that our observable universe is the interior of a black hole existing in a larger parent universe. This idea was first proposed by physicist Raj Pathria in 1972, and later developed by others like Nikodem Poplawski. Here's how it could work. When a massive star collapses, it forms a black hole. According to general relativity, it creates a singularity. But quantum mechanics might prevent a true singularity from forming. Instead of collapsing to an infinitely dense point, the matter might rebound. This rebound could be what we call the Big Bang. It would create a new expanding universe inside the black hole. From the outside, in the parent universe, it just looks like a black hole. Nothing can escape its event horizon. But for an observer inside, it would look like an expanding universe. The event horizon of the black hole would be our universe's cosmic horizon. We would never be able to see the parent universe. This idea connects to the holographic principle in a deep way. A black hole is the ultimate holographic object. All the information about its 3D interior is encoded on its 2D event horizon. If our universe is the interior of a black hole, then it follows that our universe should be holographic. All the information that makes up our reality would be encoded on the event horizon of the parent black hole. That event horizon is our cosmic boundary. This model solves several problems in cosmology. For example, it provides a natural explanation for the arrow of time. Time in our universe would flow in the direction of the collapse of matter in the parent universe. It also offers a mechanism for the creation of universes without needing a singularity from nothing. Universes could beget new universes through the formation of black holes. Our universe could be one link in an infinite chain. It also changes our perspective on dark energy, the mysterious force causing the universe to expand at an accelerating rate. Some versions of this theory suggest that dark energy could be related to the interaction between our universe and the parent universe it resides in. The holographic nature of our reality would not just be an abstract principle. It would be a direct consequence of our origin. We live inside the most information-dense object known to physics, and that object's boundary holds the blueprint for our entire existence. Number 7, the cosmic microwave background shows strange patterns. The cosmic microwave background CMB is the oldest light in the universe, a faint glow of radiation left over from about 380,000 years after the Big Bang. It's a snapshot of the infant universe. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe MAP, followed by the European Space Agency's Planck satellite in 2009. These missions mapped the tiny temperature fluctuations in the CMB with incredible precision. The standard model of cosmology, called lambda CDM, predicts that these fluctuations should be random. On the whole, they are. But the high-precision maps from MAP and Planck revealed several anomalies, large-scale patterns that don't seem to fit the standard model. One of the most famous is the axis of evil. This is an unexpected alignment of the largest patterns in the CMB with the plane of our own solar system. It's a strange coincidence that the largest features in the entire observable universe seem to be lined up with the path the Earth takes around the Sun. Another anomaly is the CMB cold spot, a surprisingly large and cold region of the sky. It's much larger than standard theories predict any single fluctuation should be. These anomalies are statistically significant. They are unlikely to be just random chance, though that possibility can't be ruled out. Holography offers a potential explanation. A team of physicists, including Kostas Skandaris from the University of Southampton, proposed in 2017 that some of these anomalies could be evidence for the holographic principle. They developed a simple holographic model of the early universe. This model described a 2D reality that then projected the 3D universe we see. When they ran the numbers, they found that their simple holographic model could explain the large-scale patterns in the CMB just as well as the standard, more complex theory of cosmic inflation. In some cases, it was even a slightly better fit to the data. Their model suggested that the apparent randomness of the CMB might be hiding a deeper, more structured order from a lower dimensional reality. The idea is that if our 3D universe is a projection, the screen it's projected on might not be perfect. Any imperfections or patterns on the 2D holographic surface would be magnified and projected into our 3D world. The anomalies in the CMB could be the first direct observational evidence of this underlying 2D structure. They could be like seeing the weave of the canvas behind a painting. This is still very speculative. The data is not conclusive, and there are other possible explanations for the anomalies. But it's a tantalizing possibility. The oldest light in the universe might be carrying a hidden message, a clue that the three-dimensional world we see is just a grand projection. Number 6, the Fermilab holometer found nothing which was something. In 2010, particle physicist Craig Hogan at Fermilab proposed a bold experiment. If spacetime is a digital holographic projection, then there should be a fundamental limit to the information it can contain. This means that at the smallest possible scales, space shouldn't be smooth and continuous. It should be pixelated, made of tiny, discrete units called Planck lengths. The Planck length is incredibly small, about 1.6 x 10 raised to the power of 35 meters. If this is true, Hogan reasoned, it might be possible to detect a fundamental jitter or blurriness in spacetime itself. This would be the holographic noise. It's the uncertainty in the position of things that arises because space itself is made of finite bits of information. You can't measure a position more precisely than the size of the pixel of spacetime. To test this, he designed an instrument called the holometer. It was essentially two L-shaped interferometers, each 40 meters long, placed right on top of each other. A laser beam was split and sent down the two arms of each interferometer. The beams were then recombined. If the position of the mirrors at the ends of the arms was jittering due to holographic noise, it would throw the recombined light waves out of phase. The holometer was designed to be sensitive enough to detect a jitter as small as a single Planck length. The experiment was a massive technological challenge. It had to be shielded from all other sources of vibration, from passing trucks to tiny seismic shifts. After years of construction and calibration, the holometer started taking data in 2014. For a year, it listened for the faint hum of holographic noise. The result, announced in 2015, was space-time appeared to be smooth, at least down to the limit of the experiment's sensitivity. On the surface, this looks like a failure for the holographic idea, but the situation is more complex. The result didn't disprove the holographic principle itself. It only ruled out one specific, simple model of how holographic noise might manifest. Craig Hogan himself said the result was just the first step. It told physicists that if space-time is a hologram, it's a very high-quality one. The pixels are either smaller than we thought, or they don't behave in the simple way his model predicted. The holometer's null result was actually a valuable piece of data. It constrained the theories. It forced physicists to think about more sophisticated holographic models. The universe, if it's a hologram, is not a low-resolution JPEG. It's an incredibly high-fidelity projection. The failure to find the noise was a clue in itself. It pointed toward a deeper, more subtle structure than the simplest models imagined. The experiment didn't kill the idea, it just made the mystery deeper. Number 5. Space-time might be made of quantum bits. The Planck scale is the smallest possible scale in the universe. A Planck length is the smallest possible distance. A Planck time is the smallest possible unit of time. Below this scale, our concepts of space and time break down, and gravity becomes as strong as the other forces and quantum effects dominate. Physicists call the universe at this scale quantum foam. It's a chaotic, roiling sea of virtual particles and tiny, fleeting black holes. The holographic principle suggests that this quantum foam is where the universe's information is stored. Each tiny patch of space at the Planck scale, a square with sides of 1 Planck length, can be thought of as a fundamental unit of information. A single bit, or more accurately, a qubit. This idea comes from the Bekenstein bound. The Bekenstein bound, derived from black hole thermodynamics, sets the absolute maximum amount of information that can be contained within any given region of space. The surprising thing about the bound is that it depends on the area of the region's boundary, not its volume. The ultimate limit is 1 bit of information per Planck area. A Planck area is a Planck length squared. This suggests that the universe has a fundamental resolution. It's like a digital image. If you zoom in far enough, you don't see a continuous picture, you see individual pixels. The pixels of our universe would be Planck areas, and each one can hold a single bit of information. This completely changes our view of what empty space is. It's not empty at all. It's a vast information storage medium. Every square centimeter of space around you can be thought of as a surface covered in a staggering number of these Planck-sized pixels, each one a potential bit of information. The total information capacity of the observable universe, if stored on its boundary, would be about 10 raised to the power of 122 bits. This pixelation of spacetime is a core prediction of many theories of quantum gravity, including loop quantum gravity and some versions of string theory. It's a direct consequence of combining quantum mechanics and general relativity. If this is true, then the smooth, continuous world we see is an illusion that emerges from a discrete digital substrate. The holographic principle takes this one step further. It says that the 3D quantum foam we imagine filling all of space is actually a projection of a 2D grid of these bits on the universe's boundary. The 3D world is built from 2D information. The fundamental reality is not the foam itself, but the bits that encode it. The universe is not a 3D space with a finite resolution. It is a 2D screen with a finite resolution projecting a 3D image. The pixelated nature of reality is one of the strongest and most direct clues that we might be living in a hologram. Number 4, dark energy is driving the universe apart. In 1998, 2 separate teams of astronomers made a shocking discovery. They were using distant supernovae to measure the expansion rate of the universe. They expected to find that the expansion was slowing down due to gravity. Instead, they found the exact opposite. The expansion of the universe is accelerating. Something is pushing everything apart. The scientists call this mysterious something dark energy. It makes up about 68% of the energy density of the universe. We don't know what it is. The simplest explanation is the cosmological constant, a value that Einstein added to his equations of general relativity and later called his biggest blunder. It represents a constant energy density of empty space itself. The problem is, when we try to calculate the value of this cosmological constant from quantum field theory, we get a disastrously wrong answer. The theoretical prediction is about 10 raised to the power of 120 times larger than the value we observe. This is known as the cosmological constant problem, and it's one of the biggest embarrassments in modern physics. The holographic principle offers a potential way out of this mess. In 2000, physicist Raphael Bousso proposed a refined version of the principle called the causal holographic principle, or the Bousso bound. He argued that the amount of information on the holographic boundary shouldn't be calculated for the whole universe at once, but rather for a specific observer's causal diamond, the part of spacetime they can see and be influenced by. This holographic approach leads to a calculation of the cosmological constant that is much, much closer to the observed value. Physicists like Andrew Cohen, David B. Kaplan, and Ann Nelson pointed out that if you apply standard quantum field theory to the entire universe, you get the huge wrong value for dark energy. But if you assume the universe is holographic, there's a limit. The total energy in a region of space cannot be so large that it collapses into a black hole. This holographic limit on the energy density of space naturally leads to a very small positive value for the cosmological constant. The calculation is not yet precise, but it gets in the right ballpark. It's a huge improvement over being wrong by 120 orders of magnitude. It suggests that dark energy is not a property of the 3D space itself, but is related to the information content and size of the universe's holographic boundary. The accelerating expansion of the universe could be a macroscopic holographic effect. The mysterious force pushing galaxies apart might be a consequence of the fundamental information limit of the cosmos. It's a clue that the large-scale structure and fate of our universe are governed by rules that are written not in 3D space, but on a 2D boundary. Number 3, a black hole's secrets are written on its skin. A black hole is formed when matter is crushed into a tiny space. Its gravity is so strong that nothing, not even light, can escape once it crosses a boundary called the event horizon. According to classical physics, a black hole is a very simple object. It's described by just 3 numbers: its mass, its spin, and its charge. Anything else that falls in is lost forever. In the early 1970s, a graduate student named Jacob Bekenstein was thinking about this. He was bothered by the second law of thermodynamics. This law states that the total entropy or disorder of a closed system can never decrease. If you throw a hot cup of coffee into a black hole, its entropy seems to just disappear from the universe, violating the law. Bekenstein proposed a wild idea. He suggested that a black hole must have its own entropy. And he said this entropy must be proportional to the surface area of its event horizon, not its volume. This was strange. In all other systems, entropy is proportional to volume. A bigger box can hold more disorder. But a black hole, he claimed, stored its disorder on its 2D surface. Stephen Hawking initially thought Bekenstein was wrong, but when Hawking tried to prove it, he ended up proving Bekenstein was right. He showed that black holes are not completely black. They emit a faint glow of radiation, now called Hawking radiation. This radiation means they have a temperature, and if they have a temperature, they must have entropy. And the formula for that entropy, the Bekenstein-Hawking formula, confirmed it. The entropy is proportional to the area of the event horizon. This was the first concrete piece of evidence for the holographic principle. It was a stunning result. It meant that all the information about everything that has ever fallen into a black hole, every star, every planet, every particle, is not lost. It's fully encoded on the 2D surface of the event horizon. The 3D interior, a region of space-time with immense volume, can be completely described by information living on its 2D boundary. This is the very definition of a hologram. A 2D surface that encodes a 3D image. Black holes are nature's holograms. They are the densest objects in the universe, and they demonstrate that the fundamental law for information storage in our universe is about area, not volume. If this principle applies to a black hole, the argument goes, why not to the universe itself? The universe, like a black hole, has a horizon, the cosmic horizon, the boundary of what we can see. If we treat the universe as a single system, the holographic principle suggests that everything inside it, including us, could be an intricate projection of information stored on that cosmic boundary. The physics of black holes provides the most compelling piece of the puzzle. It shows us that nature uses the holographic trick at the most extreme limits of gravity and density. Number 2. The universe is trying to hide its information. The black hole information paradox is one of the deepest puzzles in physics. It's a direct conflict between two of our most fundamental theories, Einstein's general relativity and quantum mechanics. Here's the problem. According to quantum mechanics, information can never be destroyed. It can be scrambled and hidden, but it's always conserved. If you burn a book, all the information in that book is still technically present in the smoke, ash, and heat. You could, in principle, reconstruct the book. But what happens if you throw the book into a black hole? According to general relativity, the information crosses the event horizon and is lost forever. It's cut off from the rest of the universe. To make matters worse, Stephen Hawking showed that black holes evaporate over very long timescales by emitting Hawking radiation. He calculated that this radiation is thermal, it's completely random, and contains no information about what fell in. So when the black hole completely evaporates, the information that fell in is truly gone. It's been deleted from the universe. This is a crisis. If information can be destroyed, quantum mechanics, the foundation of modern physics, is wrong. For decades, physicists have been trying to solve this paradox. Leonard Susskind, one of the fathers of the holographic principle, said the debate over this was a war for the soul of physics. The holographic principle offers a solution. It says the information never actually enters the black hole in the first place. It gets stuck on the event horizon. The 2D surface of the event horizon acts like a cosmic hard drive. As the book falls toward the black hole, all the information that makes up the book gets scrambled and encoded onto the surface. From the perspective of an astronaut falling in with the book, they would pass right through the event horizon, seemingly without incident on their way to the singularity. But from the perspective of an observer outside, the book would appear to slow down as it approaches the horizon, get flattened and spread out over the surface, and eventually get radiated away as part of the Hawking radiation. The paradox is resolved because there are two different complementary descriptions of what's happening. Both are correct from their own point of view. The key is that the information is never in two places at once. It's either inside for the falling observer or on the surface for the outside observer. You can never have both descriptions at the same time. This solution, called black hole complementarity, leads directly to the holographic principle. If all the information about the 3D interior of a black hole is stored on its 2D surface, then it's a hologram. The paradox forces us to accept that our intuitive 3D view of the world is not the only valid one. There is a corresponding 2D description that is just as real. The battle to save information from black holes led directly to the idea that the entire universe might be built on the same holographic foundation. Number 1, there is a map that translates the universe. The ADS-CFT correspondence proposed by Juan Maldacena in 1997 is the single most important clue. Well, it is the first and only precise mathematical formulation of the holographic principle. It's not a speculative idea, it's a concrete duality, a mathematical dictionary that translates between two different worlds. Let's break it down. The ADS stands for anti-de Sitter space. This is a model universe with a specific saddle-like curvature. It's a universe with gravity, It's similar to ours in some ways, but simpler to work with mathematically. It has a boundary. The CFT stands for conformal field theory. This is a type of quantum theory that describes physics on that boundary. This theory does not have gravity. It's a flat, lower dimensional world. Maldacena's discovery was that these two theories are mathematically equivalent. Every object and every event in the 3D ADS universe with gravity has a direct counterpart in the 2D CFT on the boundary. A black hole in the 3D space might correspond to a hot fluid of particles on the 2D boundary. The interaction of two particles in the 3D space can be calculated by looking at the interactions of fields on the 2D boundary. This is a stunning revelation. It's a working model of a holographic universe. It shows in the language of mathematics how a world with gravity and an extra dimension can emerge from a simpler, lower dimensional world without gravity. And gravity in the 3D world is an emergent effect of the quantum interactions on the 2D boundary. The ADS-CFT correspondence has become one of the most powerful tools in theoretical physics. It has been used to study everything from the properties of subatomic particles to the mysteries of black holes. For example, physicists have used it to calculate the viscosity of the quark-gluon plasma created in particle accelerators like the Large Hadron Collider. This is a notoriously difficult calculation in standard physics, but it becomes much simpler when translated into the language of black holes in ADS space. The results match the experimental data surprisingly well. This suggests the correspondence is not just a mathematical curiosity. Well, it seems to be telling us something deep about the nature of reality. While our universe is not a perfect anti-de Sitter space, it might be holographic in a similar way. The ADS-CFT correspondence provides a proof of concept. It shows that the holographic principle can be built on a solid mathematical foundation. It is the Rosetta Stone of modern physics. It provides a bridge between the world of gravity described by Einstein and the quantum world of particles. It does this by showing that one world can be seen as a projection of the other. It is the ultimate clue that the solid, three-dimensional universe we perceive might be nothing more than a complex and beautiful hologram projected from a simpler reality on a distant cosmic screen.